initial and final value theorem. We have a small statement that we need to write here for this initial and final value theorem. So let me write this so that we can have a clear understanding of what we need to know before solving this problem. So the statement is, so if the continuous time signal x of t and its derivative d by dt x of t are Laplace transformable. What do you mean by this? X of t and the first order differentiation of x of t are Laplace transformable. Means their Laplace transforms exist. Okay? The meaning is x of t Laplace transform exists and d by dt x of t Laplace transform exists. The meaning of this statement. Okay? So continuation and x of t is equal to 0 for t less than 0 and x of t has no impulses at the origin. So based on all these conditions, the initial value of x of t, that is x of 0 plus, is equal to limit s tends to infinity s into x of s. I'll tell you all this further. Continuation, the final value of x of t is limit t tends to infinite x of t equal to limit s tends to 0 s into x of s. Now I'll make you understand like what the statement means. Now the first statement, x of t and d by dt x of t are Laplace transformable, means the Laplace transform says both x of t and its first order differentiation exists. The first point, first understanding. Second one, x of t is equal to 0 for t less than 0, means this you can easily understand, right? What do you mean by this? X of t equal to 0 for t less than 0.
The x of t does not exist for negative time.
Right. X of t doesn't exist for negative time. Right. Super. Next statement. X of t has no impulses at the origin. That means you can guess it.
X of t is still 0.
Yeah, that means x of t at the value of t equal to 0 has no impulses. That means there is no sudden change. For suppose if I draw like this, at t equal to 0, I show like this. This is a contradiction which I have drawn. You can observe here in the graph that x of t is having a sudden change from a 0 level to some specific level at t equal to 0. But the statement here, it is being said that x of t has no impulses. Impulse in the sense it is sudden change. But in this graph, we observe that there is a sudden change. So what he is saying that x of t has no impulses at the origin. That means I cannot represent any sudden variation at t equal to 0. Got it? The only changes that I can make is only after t equal to 0. we can expect changes only after t equal to 0, not at t equal to 0. That's why we are talking about the x of t value. The first value of x of t starts not at t equal to 0, but at 0 plus. Can you see that?
Yes, sir.
Not at 0, but after 0. So that after 0, we are representing as 0 plus. And the final value, obviously you can see that the final value of x of t, it may extend at infinity. So we are applying the limit t tends to, we can't directly write x of infinity. That's why I'm writing it as limit t tends to infinity x of t can be found as limit s tends to 0 s into x of s. So using the, so this is the statement for initial value theorem, and this is the statement for final value theorem. Combinedly, we call it as an initial and final value theorem. But these supporting statements are needed. Until unless we don't have these supporting statements which are considered as true, you can't go for writing these initial and final value theorem statements. So the first value or initial value of x of t, that is x of 0 plus, can be found using this expression from its Laplace transform, and the last value of, or the final value of the time function x of t can be found using this Laplace transform s tends to 0 s into x of s. This is what we have to prove. So directly what I do is, there is a need for support for this actually. So this support is not needed to do in examinations. Whatever the result you get here, you can directly use in examinations. The result can be directly used in examinations while you are proving this initial and final value theorem. And the result is, so unilateral Laplace transform of d by dt x of t. This is what I am trying to solve. Okay. Can anyone try to do it? Unilateral Laplace transform of d by dt x of t. I will also start doing it. Can you please tell me what are the limits of integral now when I am talking about unilateral Laplace transform?
0 to infinity.
Nice. So 0 to infinite. And the function for which you have to find Laplace transform is d by dt x of t e power of minus st dt. So this is blindly I have substituted in the Laplace transform formula. Okay. Now can I go for, because the first function is a function of t, the second exponential is also a function of t. Can I go for integration by parts? Can you do it?
Yes, sir.
Yeah, please do. So you will get x of t, because integral of d by dt both get cancelled and you get x of t into e power of minus st. The first function remains as it is. I can choose either u or v, whatever I want to make a simplification. So the limits will be from 0 to infinite. And you have a second part also. It is minus integral of, again 0 to infinite. Integral of d by dt will result x of t, and d by dt of e power of minus st. Hope you got me.
Yes, sir.
Okay. So just using a UV rule of integration by parts, I wrote this. Now please integrate, perform the integration. So you'll observe, I'll remain this as it is, I'll do it later. I'll write this as it is, minus. So d by dt x of t, you observe that it is x of t. You'll get minus s into e power of minus st here. Am I right? You have a dt, you have a dt. Am I right till this point?
Yes, sir.
Okay. So this remains as it is minus. Now, can I take this minus s out of the integral?
Yes, sir.
So if I bring that minus s onto the other side, it becomes plus s integral 0 to infinite x of t e power of minus st dt. Now see this. This is representing the unilateral Laplace transform of x of t directly. So this can be written as plus s into x of s. So all this is a Laplace transform of x of t. So x of s. Look. Now what about the first term?
It becomes x of t.
Right? So upper limit e power of minus infinity.
Minus it
Yeah,
becomes 0.
right? And you'll get minus of x of, should I write here 0 or 0 plus? Because x of t is not having any impulse at the origin. Okay, I'll maintain that 0 as 0 plus now. So I'll be going for 0 plus here, 0 plus here, and here also 0 plus. Since x of t doesn't have any change at t equal to 0. Now, unilateral Laplace transform of d by dt x of t is, maybe I can write properly. So d by dt x of t, unilateral Laplace transform is s into x of s minus x of 0 plus. So this result I am using to prove or solve this initial and final value theorem. Is it clear this result?
Yes, sir.
Can you please compare the same result with the bilateral transform, the Laplace transform of d by dt x of t? Maybe I can go up faster and I'll show the time differentiation. Time differentiation. Yeah. Can you see here? Recollecting the time differentiation property of d by dt x of t, what is the result you got? It is s into x
Into
of
x.
s, right? This is bilateral Laplace transform we did. Whereas if you go for the unilateral Laplace transform, you got an additional term along with that. That is s into x of s. The additional term is minus x of 0 s. So all this, whatever I did, you can use. So all this part is only for your support, not needed for doing in examination while you are proving the property of initial and final value theorem. We are going to use only this result, whatever you have got at the end. Okay. Now, coming back to the
Yes, sir.
proof of the theorem. So we'll go for proving the first theorem, that is initial value theorem. Now, so Laplace transform of x dash of t or d by dt x of t. Even though I wrote here Laplace transform, it is meant as unilateral Laplace transform. Why? Can anyone tell me? Because
Because x of t is 0 for t less than 0.
right, because it was mentioned that x of t is equal to 0 for t less than 0. Even though right here this has Laplace transform of d by dt x of t. So it is clear that since x of t is equal to 0 for t less than 0, this Laplace transform is meant for finding the unilateral Laplace transform of the time differentiation of x of t. Okay. So this is what result you have got earlier, s into x of s minus x of 0 plus. This is from the result which we have derived just now. Now, what I am doing is on the left hand side, I am blindly applying the Laplace transform formula. Integral. Since there is no impulse at the origin, I am starting from 0 plus to infinite d by dt x of t e power of minus st dt is equal to just writing the same old whatever we did earlier. Okay. Now, what I am doing now is I am going to apply the limit s tends to infinity on both sides. So applying the limit s tends to infinite. What is there here? 0 plus to infinite d by dt x of t e power of minus st dt equal to limit s tends to infinite s into x of s minus x of 0 plus. Now, what happens to the left hand side when I apply the limit? You can take, how can I simplify this? You have two operations, am I right? One is limit, the other one is the integral. So I can go for interchanging the order of operations. So integral along with this, because there is no s in the first quantity, I'm taking it out. And that limit will be applied for e power of minus st and dt equal. This is limit s tends to infinite s into x of s. Limit will be applied for both quantities x of 0 plus. Now tell me what happens to the left hand side, which is the term within the brackets, this one.
0.
0, because s tends to infinity, e power of minus infinite, it leads to 0. So the left hand side has become 0. From this, you have limit s tends to infinite s into x of s, and we don't have any s term here. So therefore, this can be directly written as x of 0 plus. From this, the initial value where the signal x of t starts, that is x of 0 plus, is equal to limit s tends to infinite s into x of s. This is how we prove the theorem. Now, did you understand like why I made this support for you?
Yes, sir.
Okay. So this result we have used. So directly substituted in the formula. Later, I have applied the limit s tends to infinity on both sides. And after interchanging these order of operations, limit is applied only on e power of minus st, which made it e power of minus infinity. That's why the left hand side becomes 0. And after simplification, the initial value of x of t can be found easily by applying the limit s tends to infinity s into x of s. Now we'll go for the second part of this theorem, that is final value theorem. Final value theorem also, please do the same. See here, see the statement of final value theorem. What is the limit we have applied?
Limit s tends to 0.
Now do the same. Whatever I did here for initial value theorem, do the same. But we have to apply the limit, not s tends to infinity, but we have to apply the limit s tends to 0 on both sides. Can you do it now?
Yes, sir.
Please try on your end. I also do in parallel. So, as per the result, the unilateral Laplace transform of d by dt x of t is written as s into x of s minus x of 0 s. Now, applying the formula in finite, d by dt x of t e power of minus st dt is equal to s into x of s minus x of 0 s. Now, in the next step, applying the limit s tends to 0 on both sides, d by dt x of t e power of minus st dt equal to limit s tends to 0 s into x of s minus x of 0 s. Now, interchanging the order of operations, integral 0 plus to infinite d by dt x of t comes out, and this limit is applied on e power of minus st, and dt is coming out equal to limit s tends to 0 s into x of s minus, I am directly writing x of 0 plus because limit s tends to 0 doesn't have any effect on x of 0 plus because it is some constant value representing it x of 0 plus. Now, what is happening to this limit now? What is the value?
1.
So value is 1. So it is not becoming 0 earlier like earlier case. So 0 plus to infinite d by dt x of t, this is 1 dt equal to the same s tends to 0 s into x of s minus x of 0 s. Now you have differentiation inside the integral. So what we get is we'll get x of t with the limits of 0 plus to infinite because integration differentiation will get cancelled equal to limit s tends to 0 s into x of s minus x of 0 s. Now applying the upper limit directly I don't write it as x of infinity, but I will write it as limit t tends to infinity x of t. This is how I represent the upper limit minus x of 0 plus is the lower limit application. Limit s tends to 0 s into x of s minus x of 0 plus. And you observe that this x of 0 plus can be cancelled on both sides. And finally, the final value of x of t, which is x of infinity, please don't write, limit t tends to infinity x of t equal to limit s tends to 0 s into x of s. This is how we can prove the final value. So the base for proving this initial and final value theorem is the unilateral Laplace transform of d by dt x of t is s into x of s minus x of 0 plus based on the conditions that x of t is equal to 0 for t less than 0 and x of t has no impulses at the origin. Clear?
Yes, sir.
Okay.